It's nice to see everybody. Hello, Boris. It has been a very long time since I last saw you. Okay, so I'll just begin. I'm going to shut off my video, otherwise you'll just be watching the top of my head while I'm talking, and that's not optimal. So let me see if it lets me stop my video. There we go. The other problem is my computer might start slowing down because it doesn't like it. It seems to think that sharing screen is incredibly difficult and it gets hot. So I think it might be easier if I'm not also sharing my webcam. So here we go. I'm going to talk about realizing general linear groups as Galois groups. And I apologize in advance that to the TDLC group crowd, I'm not going to be talking about very interesting groups. So in fact, most of this talk is going to be about the least interesting groups in existence, namely finite groups. But at least you can combine them together and turn them into profinite groups, which is the second least interesting groups for you guys. I apologize for that, but I'll try and redeem myself towards the end by explaining that actually there's some infinite Galois theory that might be explored. I haven't explored it yet, but there's potential here. So we already saw in William's talk today this whole question about which TDLC groups are Galois groups. And there was this statement, well, every group, well, at least every finite group is a Galois group. And that's not very interesting because every finite group is a subgroup of Sn. But if you're asking for Galois groups, not just of some extension, but specifically of Q, then the question becomes much harder. So here we go. So it's called the inverse Galois problem. And this is one way to start approaching this whole area. And it's really this. So given a group G, let's say a finite group, given a finite group G, does G occur as the Galois group of a field extension of Q, of a number field? Does G occur as a Galois group of, say, K over Q? And this is a pretty hard problem. And in a sense, we expect the answer is probably yes. And given that finite groups, despite not being interesting from a topological point of view, can be wonderfully complicated, that really tells you that the absolute Galois group of Q is an incredibly complicated group if every possible finite group is a quotient thereof. So yeah, this is a big problem in number theory. This inverse Galois problem. So the known, like I said, I think it's conjectured that every finite group does occur as a Galois group over Q. The cases that are known, well, let's start with things like Sn and An. This is due to Hilbert, I think. And it involves Hilbert's irreducibility theorem. It's actually quite nice. Then we've got things like solvable groups. That was due to Shafarevich, I believe. What else we have? Abelian groups, of course, that's quite easy. That follows from class field theory. It's really. In fact, you can realize Abelian groups as extensions of all sorts of number fields, not just of Q. What else do we have? All right, I'm going to say something like PGL2 Z modular NZ, and this comes from elliptic curves, which is interesting. I'm going to talk a little bit about that. And actually, the sporadic groups, all but one, have been shown to occur. Sporadic groups. And that's various different authors, and that's except possibly for one of the mature groups, M23, I think it is. All right, so yeah, there's a variety of techniques and so on that go into this. So I'm just going to talk generally about how to construct nice Galois groups. There are various ways that there are people who use very clever ad hoc techniques to just construct nice polynomials that have nice groups, but hello, is this going to, there we go. But there's sort of one of the approaches to get this is to have a Galois action on certain objects coming from arithmetic geometry, such as elliptic curves, and something I'll also be talking about is Drinfeld modules. But I'm going to start with something simpler. So I'm just going to say something about the symmetric group Sn, how that goes. Simply because there's an analog of this construction that is really beautiful, and that it isn't as well known as it should be. So let's just start out in how to construct Sn as a Galois group of something. You start with, so you suppose, all right, I've got a group F, sorry, a field F. So let F be a field that you care about. And you've got alpha 1 through alpha n algebraically independent over F. And then you make a polynomial that has precisely these alphas as its roots. So that's just x minus alpha 1, x minus alpha 2, x minus alpha n. This lies in the, well, just in this function field. So this is a purely transcendental extension of f. So this is a rational function field over f. All right, and we can write this as, well, if you multiply this out, then you get, of course, the symmetric polynomials, the various symmetric functions. Let me just make sure I guess I call it S1 plus S1, which is just the symmetric polynomials, and n as your coefficients of this thing. And at the end of the day, you've got your nth symmetric polynomial, which is just the product of these things. And there's still signs, there's pluses and minuses that I'm going to ignore for now. These things are the elementary symmetric functions. And this is due to, well, basically this is due to Newton. So this is quite an old, well-known thing. And now what happens is if you take f and you join these roots, then the resulting, so take f with these roots. So this is this rational function field that I'm talking about, and you think of it as an extension over the field generated by these symmetric polynomials. This thing is Galois and has Sn as a Galois group. So this is algebraic, and its Galois group G is isomorphic to Sn. So this is a really nice way of doing it. And then via Hilbert irreducibility, you can, Hilbert's irreducibility theorem tells you that if F is a Hilbertian field like Q, it tells you that you can specialize, so you can actually plug in, say, rational numbers for these alphas, and then you get Sn as a Galois group over F adjoined these rational numbers, in other words, which is just going to be Q. And that's sort of one way to get it. So this is a generic polynomial, no relations between the roots, and that way you can, all possible permutations of these roots will be automorphisms, so that gives you the full group Sn as a Galois group. So this is a fairly standard thing. And I'm going to show you a sort of an analog of this that will give you an analog of Sn when we're dealing over fields of characteristic P, which is actually really nice. All right, so this is, but before I go on to this, I'm going to stay in characteristic 0 for the moment. I'm going to show you how GL2 Z modulo NZ comes from, how you can realize that as a Galois group of something. And so once again, I'm going to start by taking some transcendental element and then constructing stuff out of it. So let T be transcendental over Q. And I'm going to define an elliptic curve over the field QT. So let E over QT, and I'm going to explain in a moment what an elliptic curve is for those who are not familiar. I think most people probably are familiar with elliptic curves, but I don't know if I can really make that assumption. So I'll say a little bit about what an elliptic curve is. But anyway, let's pretend we know what it is. So let E over QT be an elliptic curve with J invariant equal to T. So the J invariant is actually transcendental over Q with, so J invariant, I'm going to explain what all these things mean. Invariant J of E equals T. So for example, the elliptic curve, what is an elliptic curve? It's a cubic algebraic curve. It's defined by an equation of the form, in this case, y squared plus xy equals x cubed minus some coefficient x, the coefficient 36 over, I'm picking a very specific type, minus t minus 1720. Yeah, that's where the t comes in. It's in this coefficient. And it also shows up in the other coefficient. So 1 over t minus 1728. You can do that. T is transcendental. It's not equal to 1728. That's fine. This is a cubic curve. As you can see, it's a cubic equation. So the set of solutions to this, that gives you a curve in the plane, a cubic curve, and that's called an elliptic curve. Actually, when we're really talking about elliptic curves, we're talking about projective curves. So we have to add a point at infinity to this thing as well, and then it becomes a complete thing. All right. So we've got this curve, and now the amazing thing about elliptic curves is that they have a group structure. So the points on the elliptic curve, they form an abelian group in a very interesting, non-trivial way. So what I'm actually just going to do is I'm going to steal a picture from Wikipedia and paste it in just to show you what the group structure looks like. So if you just give me one moment, I must just select my snipping tool, my thievery tool. Where is it? Somewhere, there it is. New, let's go. Sorry. And now I can paste it. There we go. So here's a very pretty picture of an elliptic curve. So let's have a look exactly at what's actually happening here. So the basic space that you can see, so the gray grid, that is the projective plane. So projective plane is just like the usual Euclidean plane, but we add some points at infinity. In fact, there's a point for each direction. So this is very similar to what we saw in the last talk, where you add directions. Well, I was actually going to expect, I was expecting to see some kind of projectivization of these TDLC groups, which is the group together union with the set of directions and so on. But anyway, that's essentially what we're doing here. So we've got the plane, just the Euclidean plane. And then for each possible slope, we add another point at infinity corresponding to that slope. And parallel lines with that slope will meet at that point. So in this picture, you can see a bunch of parallel lines meeting at a point called, confusingly called O at infinity, that blue O at the top. That is not the same thing as this. This over here, that's the usual Euclidean origin. Okay, that's not the point at infinity. But the point O at the top there, that is a point at infinity. And the red thing you see, that is the curve. That is the curve cut out by this equation. Well, any equation like this. Actually, it's not this equation. It's a simpler one. It's y squared equals x cubed plus 1. But any other cubic equation of this sort will give you a similar looking kind of curve where it points on that. Okay, so we've got this curve. This curve intersects that whole circle at infinity at only one point. That's the point O. And using that, we can turn the points on the elliptic curve into an abelian group using a geometric intersection type construction. And the construction is shown here. So we've got 2 points P and Q that are marked there nice and blue in the bottom left. And you connect those 2 points, with a straight line. And because the curve is a cubic curve, and I'm going to assume I'm working off an algebraically closed field here, so we can solve equations easily, that straight line is going to intersect the red curve in a third point, because it's a degree 3 curve, right? That third point is R. But that R, that is not P plus Q. That wouldn't work. That does not give you a group structure. Instead, we now connect this point R that we made by intersecting, and we connect it to the point at infinity, and then by connect, I mean you draw another line from R to the point at infinity, the point O at the top. And once again, because we're dealing with a cubic curve, there is a third point of intersection. That's this point over here. And that is P plus Q. So this plus operation actually turns all these points on the red curve into an abelian group. And the identity element of the group is in fact the point O, the point at infinity. That's the identity. So it turns out that basically E, so points on E, together with O, well, by definition. So by E over some field F, what I really mean is solutions to, so points X, Y, and F squared, satisfying this Y squared equals whatever you want to call the equation. in this case, x cubed plus 1, but upstairs I've got a slightly more complicated equation. So I'm going to use a more complicated one, but it's a similar picture. Plus xy equals x cubed plus something x plus something else, right? Union with the point O, which I'm going to write in curly O, so that's a point at infinity. That is, hang on, sorry, I've got my research assistant trying to tickle me while I'm talking. This is really funny. It's probably good that the camera's off. Sorry, I apologize for that. Okay, so this is E of F. This is E of F, all right? And this forms an abelian group. Should make a capital A here. Abelian group with this O as identity. Okay, so here we have a nice group structure. And now what we can do, given such an abelian group, you can ask for, so you take n and you look at all the n torsion points. So this is points of order n. So that's all points on E for which n times p, which means p plus p plus p n times, is equal to the identity element. So this is really just p plus so on, p n times. So this is a subgroup of order n, and this is going to be isomorphic to z modulo nz squared, at least if the characteristic is not, if n is not divisible by the characteristic of the field. The characteristic. Otherwise, there's some points missing. I'm not going to go into that just yet. Does not divide n. So this is a very beautiful set of points. Now what you can do is this whole intersection business, if you look at it very carefully, this is actually defined over whatever field you're talking about. So if your equation for the elliptic curve is defined over some field f, then this procedure for adding 2 points, say whose coordinates are defined in f, will again give you a point p plus q whose coordinates are once again in f. So in fact, this EF, it's an abelian group, even if f is not algebraically closed and so on. So this is true over an algebraic closure. So over if f is algebraically closed and f is not algebraically closed, then the group of n torsion points is going to be some kind of subgroup of that. But let's just talk about over the algebraic closure. Now what you can do is you can have the absolute Galois group of your field f will permute these points. And so you get a Galway representation. So what you get is that, say, the Galois group of f, let's make no assumptions of the characteristics. So I say f sep, the separable closure of f. This thing acts on these n torsion points. And so that gives you what's called a Galway representation in rho sub En. That goes from this Galois group, let's just call it G. GF is probably good. GF onto automorphisms of En, but En, that's really just pairs of things in Z modulo NZ. So this is isomorphic to GL2 Z modulo NZ. Okay, so what happens is the image of that is going to be some subgroup of GL2 Z modulo NZ. And so you will find that the Galois group of, this is in general, you've got your field F, you adjoin to it the coordinates of all n division points. So the n division points that live, say, in some algebraic closure, they're algebraic points over F, you adjoin them all to F, and the resulting thing is going to be a Galway extension of F itself, and its Galway group is going to be isomorphic to the image of this representation, whatever that is, in GL2 Z modulo NZ. Okay, now the nice thing is, for different n's, these subgroups of n torsion points are all compatible in such a way that you could take the projective limit. So you can take projective limits and thereby get a Galway representation. It's called the adelic Galway representation from this group into automorphism group of all torsion points. I should really know, not into the automorphism group of the Galway of that, but instead you take automorphism groups into projective limit over all of these things, which is called the Tate module. And that turns out to be GL2 of Z hat, the profinite completion of Z. So if you're finding this a little bit daunting, you can also instead have, so this is, let's call it rho hat. You can instead have rho E P hat for any prime. You go into automorphism and you just look at a simpler kind of construction. You just look at P power torsion points. And when you do that, you will, instead of getting all of Z hat, you just get ZP, the p-adics. So this is the usual thing. So you get Galois groups that are subgroups of GL2 over some finite ring, and then things are compatible in such a way that taking projective limits allows you to get Galois groups over a ring of characteristic 0, which is nice, something like ZP. But still, these are compact disconnected groups, so they're still not as interesting as you would like, but it's better than nothing. Okay, so this is a general thing for any elliptic curve over any field F. I'm just assuming that the characteristic of the field does not divide the n that you're talking about here. So for example, take characteristic 0. Now, if I just go back to this particular elliptic curve, so remember I've chosen T to be something transcendental. T stands for transcendental, and I make this elliptic curve. Then there's a theorem, and this is actually an old theorem due to Weber. That says that in this particular case, these Galway representations are surjective. Sort of in this case. For any n from G, Q, T, so the absolute Galway group of Q adjoint T onto, GL2 Z modular NZ for any n is surjective. In other words, you get GL2 Z modular NZ as a Galway group over Q adjoint T, just the rational function group over Q, is surjective. Okay, so this is from the 1890s, I believe. It's quite an old theorem, and it uses results using modular forms and that sort of stuff. So this is really nice. That means that GL2 Z modular NZ, and by extension GL2 of Z hat or of ZP, can be realized as a Galway group of an extension over QT. Now you'd think this is brilliant. Now we use Hilbert irreducibility. You plug in nice values for Q and you get them as extensions over Q. But it's not that simple, because there's not what we call a regular extension. So in fact, if you join the n torsion points of an elliptic curve, then you are gaining for free the nth roots of unity as well, so that your constant field actually grows in the process. So it's not a regular extension. I don't want to go into this. But still, this is sort of a really nice kind of construction that allows you to create things like general linear groups using elliptic curves. And as a bonus, we learned a little bit about elliptic curves. Alrighty, so I now want to talk about a characteristic P thing. So this is sort of my thing that I spend my time on, is characteristic P. So now let K be a field containing, say, FQ, the finite field of Q elements, and Q is a power of P. Of a prime P. So the first thing I want to do is I want to show you an analog of this trick of how you use a generic polynomial to make Sn as a Galway group in the case of Q, whereas now in the case of some kind of extensions of K, you can find Galway groups that are sort of an analog of Sn. So what is a good analog of Sn? Or is there an analog of Sn? And it turns out it's in fact GLN over FQ. And I'll say something very silly about why that's an analog. So this construction I'm about to show you is due to E.H. Moore. Eliakim Hastings Moore, also end of the 19th century. So this is old stuff I'm explaining. So first of all, let's just consider the notion of something called FQ linear polynomials. So because FQ is contained in our field, polynomials are FQ linear, not just if they're degree 1 polynomials, but there's a whole lot of FQ linear polynomials. They're things of this form. F of x equals some coefficient x, some other coefficient x to the q, something else x to the q squared, and so on. So if the exponents you allow are all powers of q, well, that is in fact linear. So what I mean by FQ linear is that if you have f of x plus y, or even better, ax plus by, where a and b are in your finite field, then this is just a of x plus b of y. So you can take out constants in FQ and you can break up sums. And this is because of the whole freshman's dream. Remember, raising to the power of q, that is in fact a linear operation in characteristic dividing q. So the usual joke is don't tell this to your first year students or they will get a whole lot of things badly wrong. All right, so these are FQ linear polynomials, which is now, so this is the special thing in characteristic P that you have these things. And so what I'm going to do is I'm going to construct something like a generic FQ linear polynomial. And the way I do it is, once again, just like with the case when I constructed Sn as a Galway group, I started out with generic roots, which are algebraically independent. I'm going to do the same thing here, except now I'm going to construct a polynomial. It's going to be an FQ linear polynomial whose set of roots isn't, well, for any FQ linear polynomial, the set of roots is in fact an FQ vector space. That's easy to see. So I'm going to basically write down a generic FQ vector space of dimension n, and that'll give me one of the generic polynomial of this sort. So I'm going to choose v1 through to vn. This is going to be the basis for my vector space. So these are going to be algebraically independent over. I called my field little k. Did I want to call it little k? Yeah, okay, I'm stuck with little k, so let's call it little k. So let's take v1 through vn algebraically independent over k, and we let v be the span over fq of these guys. So that's just the vector space spanned by these. So that's just fq to the n. It's just an n-dimensional vector space with these basis elements. And then I construct a polynomial, a monic polynomial whose roots are precisely capital V. Sorry, this would be a big V. Let's make it bigger. Okay, so fx is just going to be, take a product, x, sorry, my x should be capital, right? I'll use a capital X. And then I've got all possible linear combinations, a1, v1, plus up to an, vn. For these a's, they're all line in FQ. Okay, so this is a sort of monic polynomial whose roots are precisely capital V. And this lies inside the field, well, little k adjoin v1 up to vn. A nice way of constructing this, and this is another reason I want to show this off, is you can write this as a quotient of Moore determinants. And I'm saying this because the Moore determinants are a wonderful thing that I really want to, and I think people should know more about. So a Moore determinant of something, you just give it a bunch of elements, is this determinant. It's like a van der Monde determinant, except that it's sort of the FQ vector space version of it. So you've got n elements, little x, that are in your field, and then you make columns where you've got powers of these things, just like van der Monde, but not any powers, but q power powers, like so. And then x1 q squared until you get to x1 q to the, it's an n by n matrix, right? So my highest power is going to be q to the n minus 1, and here I've got x sub n q to the n minus 1. This is called the Moore determinant. And it's a beautiful construction because it has this property that this thing is 0 if and only if the x's are linearly dependent over FQ. That's not very hard to see. Okay, so if there's a linear dependence between the x's, that means there's the same linear dependence between those columns, and so the determinant is going to be 0. And well, conversely, if the determinant is non-zero, then there can't be such a, then the columns can't have a relation, but whatever relation a column might have is the same as a relation that the x's themselves might have because of the way the qth power works. So this is actually a very beautiful thing. So this is called the Moore determinant. And so what I do is I make two Moore determinants, one with n plus 1 by n plus 1 matrix, where I take my v's in the first n columns, and the last column is just powers of the variable x, and I divide by the sort of the subdeterminant, the minor, the first minor, simply so that the resulting thing is once again a monopolynomial. But then the result is, of course, it's a monopolynomial of the correct degree whose roots are precisely the vector space spanned by the v's. So that is the polynomial that I've just made. And the theorem due to Moore is that, just like with the case of basically Newton's result about the Galois group of the generic polynomial in characteristic 0 that I had, well, it's not just, yeah, let's just say characteristic 0 to be careful. But so the theorem is that this thing has the biggest possible Galois group. And it works as follows. If I construct the Galois group of, now I've got my field, I must be a little bit careful. Okay, so K adjoin V1 through to Vn. And that's over, I should probably write down what the coefficients of this polynomial are. So this is basically going to be a G naught x, sorry, capital X, plus a G1 x to the q plus Gn x q to the n, like, sorry, minus 1 plus, it is monic after all. So the Gn is in fact equal to 0, is equal to 1. Okay, so if you take those G's, G0, G1, up to Gn minus 1, again, they have to be algebraically independent, just like the symmetric polynomials, the Newton polynomials have to be algebraically independent. The reason for that is just a question of looking at the transcendence degree. K adjoin those V1 through Vn, that obviously has transcendence degree n over K. That's by definition, they're algebraically independent. And then the subfield K adjoin G0 up to Gn, up to Gn minus 1, that has to be it has to have the same transcendence degree, because this extension I've written here is obviously an algebraic extension. But I've only adjoined n elements, so they have to be algebraically independent, because the transcendence degree has to be n. So that's quite simple. But this so it's an algebraic extension of rational function fields, basically. And the Galway group is isomorphic to GLN of FQ, which is really nice. So I say this is the analog, because there's this little joke that there exists such a thing as a field of one element. Some people don't think it's a joke, but basically GLN, sorry, what was I saying? That the symmetric group Sn is basically GLN over the field of one element, which of course doesn't really exist, but people are hunting for something that pretends to be a field of one element. And they generally agree that the general linear group over that whatever field thing is actually just Sn. So this is really in some sense, this theorem of Moore is an analog of the result of, that's ultimately due to Newton, about how to find Sn as a Galway group. So here, generally, if you look at any kind of FQ linear polynomial, just once again, the kind of like the thing that I've written here, its roots are always going to be an FQ vector space. So whatever automorphism, whatever permutes these roots, is going to have to preserve the vector space structure. So it's going to have to be a subgroup. So the Galway group of such a polynomial is going to have to be a subgroup of GLN. And so what Moore's theorem says is that if your basis is algebraically independent, or conversely, equivalently, if your G's, your coefficients, are algebraically independent, then the resulting extension is going to have the biggest possible Galway group that it can be, GLN of FQ. So this is really nice. All right, so this is GLN over FQ, but how about GLN over something more interesting than FQ? So this is where Bianca had come up with an idea. So this is, wait, I'm still writing in purple. I want to write in black. So this is not quite so long ago anymore. This is Abianca 2001, roughly. Is Abianca. He has a much more famous conjecture called the, well, Abianca's conjecture, but that's not what I'm talking about. I'm talking about a much less known conjecture, which he called the generalized iteration conjecture. Okay, and so his idea is to use something like Moore's construction, but he wants to get something more interesting than FQ as coefficients in GLN. So here's what we do. We define A to be FQT, the polynomial ring. T, once again, is transcendental. That's why it's called T. So this is a polynomial ring of FQ. And those who know me know that I love function field arithmetic. And so this is really an analog of the integers. Analog of Z. So it's also a principal ideal domain. All its quotient rings are finite. It has infinitely many primes, by which I mean monic irreducible polynomials, and so on and so on. The Riemann hypothesis is trivially true in this ring because the zeta function doesn't have any critical zeros. And as a result, you get a really super strong form of the prime number theorem. All of these things hold. So there's a huge amount of number theory that can be done over this, basically replacing Z by FQT wherever you see it. And if you're super sophisticated, well, actually just a little bit sophisticated, then you can, there are slightly more general rings A that one can use instead of this polynomial ring. So affine rings of a curve minus a point, basically. But I'm not going to talk about that. I'm just going to keep it very simple. So this polynomial ring is really nice. And so Bianca's idea is the following. Is he's going to construct a special polynomial. He's going to call it phi sub t of x. And it's going to work as follows. So it's going to take t as the constant coefficient. And then he's going to take a bunch of g's for the remaining coefficients. So all I've really done is I've renamed my g naught into t. So basically think of it as g naught is the same thing as t. But otherwise, we still have these g's algebraically independent. So still t, that's a comma. And the g's are all algebraically independent of fq. In fact, you don't have to take FQ. You can take any field containing FQ. But I'm just going to talk about FQ to keep things simple. G1 up to Gn minus 1, still n elements algebraically independent over FQ. Right? So we've got this polynomial. We know what its Galois group is. By Moore, this is GL2 of FQ. But now, in order to get a polynomial whose Galois group is more interesting, I'm going to iterate this construction. So I'm going to pick a random element A, a polynomial A, which is going to be A naught plus, say, A1t plus, what I'm going to call the degree of this thing, M maybe. A sub mt to the M, that's an FQT. I'll just write FQT. And I will construct f sub a of x, a polynomial that's basically made by iterating. So it's going to be a naught phi sub t, the phi sub t that I've got over there, and then a1, sorry, there's just a naught. Beg pardon, like so. And then there's going to be an a1 phi sub t of x. So wherever there's a t, I put a phi sub t, but now when I have a t squared, I'm going to iterate this. So instead of just squaring this thing, I'm going to compose it with itself. Because if you look at all these linear polynomials that we've got, they actually form a ring where multiplication is composition, but it's a non-commutative ring. And that's a sort of a very interesting construction. So I'm going to go all the way to am, and I'm going to compose this m times m copies of x. So this is a pretty complicated kind of polynomial. And then the conjecture was is that the Galway group of this particular thing, phi a over the field, say f, which is going to be fq, adjoin all of these coefficients, is in fact isomorphic to GLN of A modulo NA. So this is just like GL2 Z modular NZ. Think of it like that. So A is like, so A in the polynomial ring, that's my analog of Z. And sorry, this N should be an A, of course. And elements of it are like integers. And so Z modular NZ now corresponds to A modular little a. And this is how you construct these sorts of general linear groups over rational function fields of FQ. And not just FQ, you can replace your FQ by any field that contains FQ, provided your T's and G's are still algebraically independent. So that was conjectured in 2001, and in fact, it's a theorem. So everybody should at least state a theorem of their own. This is my theorem. It's from 2016, as this is true. And the reason it's true is because this really is an analog of Weber's theorem. So what Abianca constructed without knowing it is something called a Drinfeld module. Well, calling this the reason is it's a bit of an abbreviation. So basically this Abianca's phi is what's called a rank N Drinfeld module, Drinfeld FQT module. And what he's basically done here, so this Galway group that he's talking about, that is, so, okay, to explain now in the last 10 minutes what a Drinfeld module is, I can give you an idea of what a Drinfeld module is. So the interesting thing here is that Abianca didn't know about Drinfeld modules. So Drinfeld modules were introduced in the 1970s by Drinfeld. He won a Fields Medal for that because he used them to great effect for the Langlands program and so on. But Abianca didn't know about these things. So he made this construction through his intuition, and it was part of his quest to find nice equations for nice groups. And he inadvertently rediscovered Drinfeld modules, essentially. Okay, so what is a Drinfeld module? So once again, remember these FQ linear polynomials. I'm going to call it, so if you've got a K, so K is our field. Let me just see what I want to do. Okay, so K is a field containing FQ. And what I'm going to do, I'm going to look at this is the set of all FQ linear polynomials over with coefficients in there. So I'm going to write it like so. So this is really all FQ. Well, let me write out. Remember what FQ linear polynomials look like? They look like so. A naught x plus a1 x to the q plus up to a, there's some degree, it's not fixed, q to the n, where your ai's are in k. This set of all these things forms a ring where multiplication is composition. So forms a typically non-commutative ring under composition. Well, the multiplication is composition. This is commutative if k is actually fp for a prime p, but that's not an interesting case. So in general, this k can be an infinite field. That's fine under composition. And now a Drinfeld module is basically something like what Abianca constructed. So this is not the most general definition, of course, but that's okay. A rank R Drinfeld A module. This also works for more general definitions. A is basically a ring homomorphism. So I'm going to write down a purely algebraic definition. So phi from our commutative ring A into our very non-commutative ring of FQ linear polynomials. And the way it works is, well, T gets sent to something that looks like so. And there's really just two conditions. So basically, it's a ring homomorphism from this commutative ring A into this big non-commutative ring KXQ. And the only two conditions are that A, the linear part is in fact T itself. And secondly, you also have higher powers appearing. That's it. That's all you need. So G to the, basically, there's R of them. And that R there is the rank. these GIs are in our field, whatever that is, and the last coefficient mustn't be 0, so that the degree really is q to the r. So what we've got over here, there are, that's called the rank. And the important thing is that, okay, that's at least 1. So that's a sort of a non-triviality thing. So higher powers, so actual q powers do occur. And the linear part is just multiplication by t. So that having the linear part being multiplication by t is just a normalization. If you have another ring homomorphism that doesn't satisfy this, just divide it, and you can make this happen. And so all we really want is non-trivial ring homomorphisms. And that's a Drinfeld module. And the amazing thing about Drinfeld modules is they are purely algebraic objects like this, but they really try very, very hard to pretend to be elliptic curves. And they have incredible properties that are analogous to properties of elliptic curves, from their torsion submodules through the theory of complex multiplication, all the way to defining things like modular forms. It's all there. It's amazing. Specifically, the rank 2 Drinfeld modules behave just like elliptic curves. Higher rank behaves sort of halfway between elliptic curves and abelian varieties. So to understand why this is in any way analogous to an elliptic curve. So geometrically, this is really not very interesting at all. So geometrically, what we've got is sort of a Drinfeld module like this, really just defines a novel A module structure on the field. So I'm just going to say on GA, the additive group over the field. Okay, because this thing here, the FQ linear polynomials, those are precisely the FQ linear endomorphisms of the additive group over the field. So from an algebraic geometry point of view, this is incredibly trivial. It's really just the additive group. It's a straight line. That's all it is. It's an affine line. So whereas an elliptic curve, this cubic curve is actually a genus 1 curve. It's great. But this straight line is genus 0. It's not interesting. But what it does have is, because we have this Q power map that gives you additional endomorphisms, you still have an interesting structure on this. And so this A module structure, it's actually quite simple. So you've got an element A inside A, and you've got some X inside your, let's just say inside your field. Then A star X, the action of A on X is simply you take this polynomial phi A that you can make. So remember that phi is a ring homomorphism. What I've defined, what I've said there is just what happens to T. And then by linearity, because T generates A, this tells you what phi does with any element. So you have a phi sub A, the image of, so in general, you've got A, and the image of A is called phi sub A. It's a polynomial with a variable X. And then you just plug your element of the field into that. So you plug it into the polynomial. And this turns out to be an A module structure on K. But it's not the usual A module structure. So K might, for example, contain A. In fact, I'm assuming it here. So I'm assuming that K contains this. I don't have to assume this. I just need a map from A into K, and then you can talk about finite characteristics and stuff. But that's, I don't have time for that. Anyway, so typically A is a sub-ring of K. So of course it's an A module in a trivial sense, just multiply by the element A. But this is a different A module structure. It twists things. So it's really very interesting. And now you can ask for stuff like the torsion. Sort of just like the points of order n on an elliptic curve, you can take an element A. Remember, a little a is just like a little n, like an integer. So I think of an a as basically being an integer. I can talk about the torsion. So here's my module, and I talk about that. All that really is just the kernel of phi sub A. So the things that get killed, it's the roots. It's the set of roots of phi sub A, but it is in fact a submodule. So kernel this, which is really just, I'm going to take the algebraic closure such that phi A x is equal to 0. This is in fact an A submodule, and is isomorphic to A modulo AA to the power of the rank. So if the rank is 2, that's like Z modulo NZ squared, which is what the N torsion subgroup of an elliptic curve looks like. So it behaves a lot like an elliptic curve. And in the case of rank 2, you also have something like a J invariant that behaves, and so on and so on. It's really very beautiful. But because you have the structure, once again, you have the take K sep, and the Galois group of K sep over K. So this, once again, the absolute Galois group of this acts on phi A. So once again, you get Galway representations associated to phi and associated to A that takes this absolute Galois group and makes it act on here. So it gives you a group homomorphism from this absolute Galois group to the automorphisms of phi A. But the automorphisms here, this is just after you've chosen a basis, it's going to give you A modulo GLR of A modulo A little a. And this, of course, is precisely the Galois structure that Bianca had gotten at. Except, of course, in general, for a Drinfeld module, we're not assuming that these G's are in any way algebraically independent of anything. They're anything. They're coefficients. They can be defined in FQ. It doesn't matter. But always the Galway action, it exists, and it will give you this kind of Galway representation. So you can take your field, your ground field, you adjoin all the roots of this polynomial. What you get is then the splitting field of the polynomial phi sub ax. That's automatically, it's Galois, so it has a Galois group, and the Galois group is going to be a subgroup of GLR A modulo little a. And so the trick is to show that if your coefficients defining the Drinfeld module are algebraically independent, then this Galois group is going to be as big as it can be. And that's sort of what I showed. The ingredients, so my proof is not at all like Weber's theorem. It's different. I use properties of moduli spaces of Drinfeld modules. So there's some algebraic geometry that goes into it. So here's the trick. So if the coefficients defining the Drinfeld module phi are all algebraically independent over some base field, say over FQ, or FQT, I want it to be independent of T as well, then this Galois group, the image is as big as it can be. As possible, basically. And in fact, so my theorem says that this rho then phi, this thing is surjective. And the ingredients are basically lots of algebraic geometry. Geometry of basically moduli schemes of Drinfeld modules. Say moduli spaces to be less pretentious. Of Drinfeld modules. I'm sure I can fit this on one page. So what you've got is the moduli space. It's a sort of it's a geometric creature that somehow parametrizes the variation of Drinfeld modules. And to make things nice and rigid, you add a level structure. And then you've got the moduli space of Drinfeld modules of rank R with a certain level structure. And then for different level structures, you've got maps between them. And the important thing is that for the maps between them, those are then Italic extensions, and they have the correct Galois group. This was proved by Drinfeld back in the 1970s. And then I use that as one of my ingredients together with description of exactly what happens when the situation of level T structures or level T to the n structures can be described more explicitly, and using a lot of that. So that's how this comes from. So at the end of the day, why could this possibly be interesting to you? If you guys really love totally disconnected locally compact groups, and I've only really talked about finite groups here, and at best pro-finite groups, because once again, these things are compatible. I basically get a surjective map onto GLR of A hat of the pro-finite completion of this polynomial ring A. So the question here really is, what have I done? So at the bottom, I've got FQ, and then I've got, say, FQT, and then I've got FQT adjoin these various G's, which are algebraically independent. And then I've got, let's call this big K. And then here I've got K, and I adjoin the torsion points of that. And all I've shown here is that over here, I get a finite group, GLR A modulo little a. But maybe since these extensions, the other extensions are transcendental, you could ask, what sort of Galois groups do you get here? And those might be interesting groups. So for the people who are interested in infinite sort of Galois groups of transcendental extensions and so on, maybe this is a place to start looking, and maybe there we can find something interesting. Okay, I think I'll stop here. Thank you very much.
Thank you, Florian. Are there any questions?
Yeah, I want to ask you a question related to your last statement. So as far as I understand, you want to get a sort of a number of analogs of results in inverse Galois theory you mentioned in the beginning of your talk. So what's the current status of this inverse Galois problem in this setup for, say, for FQ of T? What's known apart from small examples or whatever?
And this is where all embarrassed because I actually don't know. I use the inverse Galois theory more, inverse Galois problem more as a hook to try and, as one way to motivate the definitions that I'm bringing. I don't actually know that much about which results are known. Okay. It is an interesting question. So obviously there are people who do study this, but I can't actually tell you which sort of results are known in this case.
Okay. Thank you, Florian.
Okay. Any other questions? Also, if you don't want
to.
Yeah,
can I ask, sorry, can I ask a question about the last remark as well?
Mm-hmm.
So the extension on the top there, or the group on the top there is a finite group.
That's right.
And the other extensions are transcendental.
These are purely transcendental, yeah.
Yeah.
So maybe
it's
something
sort of looking like this is a discrete group. Is that right, or am I missing something?
In the Netherlands, not in Switzerland.
No, the other one is not.
Sorry.
I don't actually know what the more. I mean, I don't know. I haven't until now thought about infinite Galois theory at all.
Yeah, if it's a finally generated extension, you get a discrete group.
Yeah.
Okay, so then that's not terribly interesting at all. I mean, that's finitely generated.
So if can you do this sort of thing and make your top group profinite?
Yes, I can do that.
That might be a way to get.
Yes, absolutely. That still works. So then he's the same. This is just a rational function field. G1, GR minus 1. And then over here, you can adjoin instead the Tate module, which is really these guys. And there you're going to get GLR of A hat, for example. It's a nice big group.
Mm-hmm.
And maybe now this thing over FQ or over FQT is a more interesting extension. I don't know.
Okay. Do we have any other questions for Florian?
Yeah. Can I ask something? I think we've seen a similar example also in the first talk, or when we looked at the elliptic curve, right? And then he realized the multiplicative group of Q as a quotient inside, wasn't it?
You mean the previous talk?
In the previous talk, yeah. Is something like this happening here as well?
That's a good question. So what did we have in the previous talk? We had various P power roots of T, right?
Yeah, it was the flat rank, right? That he constructed a subgroup which had a homomorphic image Q times, or the positive part of it, right? Yeah, is something similar happening here as well? Do you have big abelian sections in this?
Well, certainly you can take rank 1 and then you get, just A hat star here. So that's then going to be abelian in the,
Yeah.
The rank 1 Drinfeld modules. In fact, that's known as a Carlitz module. It's known since the 1930s. Carlitz. So that's already interesting. So if you, but once again, that is just this portion, the finite portion, the only part I've ever cared about until today.
Yeah.
So then if you look at the Galois group all the way down to FQ, I don't know. I mean, that is just a question of, what other automorphisms do you have? You can move the G's around. You can move well, there's no G, right? There's no G's. It's just FQT. You can move the T's around. So that might give you That is not, in fact, if you adjoin torsion of the Karlitz module, that's not so different to adjoining p powered roots of t, which is essentially what was going on in the first talk, as far as I made it out. So that could even be something very similar. So in fact, so in the rank 1 Karlitz case, what you've got is your Drinfeld module phi tx is simply tx plus x to the q. So what you're adjoining, it's not the same thing as literally taking roots of t, but it's sort of analogous to. So if you look at torsion, which, yeah, the question say t to the n torsion. What is that? So that's going to be roots of yeah, basically phi t composed with phi t. It gets kind of complicated with the actual coefficients and what this thing looks like. Phi tx equal, yeah. And this is sort of analogous to the case of, it's not quite p to the n, but it is a little bit like analogous to the roots of the multiplicative group, you know, torsion of the in torsion of just the multiplicative group. So basically roots of unity. In fact, this whole Karlitz theory in rank sort of adjoining torsion points of rank 1 Drinfeld modules that gives you Abelian extensions, like I just mentioned, and that basically gives you explicit class field theory of FQT. And that's essentially analogous to adjoining roots of unity, but it's not literally adjoining roots of unity, because those would be constants, those would just be extensions of FQ. So these are things that behave a bit like roots of unity. So it's maybe not so different, analogous to, should we say, roots of unity.
Yeah.
But it's not quite the same as roots of t, right? So, yeah. So maybe what you would want is something like adjoin roots of things like phi t n x minus t, right? Those would be Karlitz roots of t. And maybe that gives you some interesting, I'm not sure, but now it's not quite clear what the structure, well, you still have a kind of a, you still have the phi t action on this. So maybe that's what one should look at. Maybe look at taus of this. Of course, that is no longer FQ linear, but you really are looking at pre-images of T under the Karlitz T action. And so that might actually, that might indeed have interesting color roots. So maybe this is worth looking at.
Yeah.
Well, do we have any further questions apart from possible directions for further research? If not, we can thank Florian for his talk one more time.
Thank you.
And if people are interested, we can still keep rolling for some conversation.